Somehow I'm like cramming in all this stuff on a Friday, but I've been on schedule so far. We actually started at 12:20. I was expecting to be like a little late with everything else going on for today. I don't know if everybody else has had a Friday like this, but it's just been like back to back to back to back. But now here we are, doing some dynamics, something fun for a change. Oh, but we have no screen. That would help. Projector on, monitor on. It's coming. We'll be here. Last time we left off with a cliffhanger, looking at another vector, trying to measure locations. And again, like everything, at least kind of intro to Newtonian mechanics, everything's a vector. Like you're just always dealing with vectors. Even when we deal with like torque and that kind of thing, cross products, we still end up with vectors. So being able to switch from one system to another, it's kind of the core, the baseline stuff of what we need. So that's why we're doing it a few times, figuring out when you define one thing, how do you switch into some new coordinate system. So we figured out on Wednesday that if we go 2.3 meters along the E1 and 3.1 along that E2, we end up at point P. So today, the question is, how far did we have to travel? Like when we traveled in that same way, how far did we go along this A1? Give me that. And how far did we go along this A2? So it's got to be the same vector. It's got to be the same magnitude. It's got to have the same direction, but we're changing how we're looking at it. So I want to know, we did this once before, so now I want to know how you're approaching it. Are you using linear algebra? Are you doing some trig? Are you just sort of like waiting for the answer to appear? Sorcery, Lagrange multiplier. What do you think?
I mean, I think we're going to have to do this similar.
Okay. Yeah.
Cosine sine points of both of the, both of the other vectors we need to.
Okay.
And to get to point B.
Yeah.
So we can probably watch
Oh, like trying to figure out. So yeah, you can either the cosine is definitely like sine and cosine.
yeah. And yeah, this one's just because just get this
Yeah, like that 2.3 is definitely going to have some cosine along that 30 degree for sure. But there is a sine.
Yeah.
30 on that 2.3 together.
Is that the first one?
Okay. First one was 100.
Yeah.
Yes, that vertical one was.
Yeah.
Yeah. Not one. Oh, the brain. Yeah.
This doesn't really look like what it feels. Because A1 is right?
What's that?
Like it's a triangle.
Oh, no, some usage.
Alright, so then
Special unit map. This is
plan one issue vertical line, trying to figure out that horizontal. Are you trying rotation matrix again? Yeah. It's kind of taking step back. Now
very good.
I woke up because they turned the heat on in the building, and suddenly the yeah, I thought someone was back here.
oh, okay, alright. This sounds great.
She doesn't.
No, that's what you're saying.
Oh, okay, yeah.
But yeah, in the it's like prime time. Well, see, he's a good
Yeah, what were you thinking?
He's got the right. I mean, it's not like always every time. That one makes more sense. It's a cure.
Yeah, so if you think of it that way,
And then trash.
have a vector, you want to maintain the vector, so you don't want to change its size, like you don't want to do two response, so you're trying to look at the rotation to
Yes.
there is a rotation matrix that you can use. And that will transform.
Where am I right now? Oh,
Yeah, that's cosine data. Maybe
okay.
sine data. Sine data.
Yeah. So you just go down.
Yeah. Now, yeah, you can
Oh, you just go down. Yeah.
That's just like past 2 years, original, got it rated 2, we didn't really talk about
Yeah.
like going on the insurance.
Yeah.
So like I'm kind of about that. Yeah, that would work.
Do you have it?
No.
If you only take a rise in there, then you can always involve the contact. If you ever need to write process.
I should. All
Okay.
okay.
Oh, shit. Okay.
Yeah.
Yeah. I've got consistency. I was here that day. I did a couple of times last year. It's just about it was a lot steeper than I remember, but a lot
Find that magnitude, and now really what you're doing there is you're taking the top values and navigating
yeah. No, like, what have you heard? Once it gets paid, I just read my sister every time. I can't. Yeah, I'm just trying to Oh,
if we did a clockwise rotation, it would be 30 plus 50. But we did a counterclockwise. So yeah, if we rotated by 53 degrees, the angle would stay around. Yeah. Right. So we would only have an A branch. That makes sense. Yeah. The process is exactly what it's the right process that you're thinking. Yeah, so you can take 50 minus 30, and that's your new call it theta alpha or whatever. Yeah. Oh, to find out those new unit vectors in terms of A1 and 2. It's a good start. Here, is this All right, so I'll start off with the same approach that we ended up with last time, where I define new unit vectors. It's like E1 is a direction, A1 is a direction, so both of them are like magnitude of 1. They're just pointing somewhere. So if I want to describe E1 in terms of A1 and A2, it'll be oh, I don't know why I did that. So I can just create like a math definition of like this vector is sines and cosines. Like in order to go one step along that E1, I have to go out of my way along A2 in the negative direction, then up positive cosine theta along that A1 direction. And then E2 is similar, but it's going to be like a sine 30 along that A1 plus a cosine 30 along that A2. And there's a few people in the class that are like, I know these vectors, like it's linear algebra somehow. Really what I'm doing is defining like a linear algebra rotation matrix. You don't have to do this, like if you're not interested in linear, it's a super valuable skill to have is linear algebra, but I get it. Like at first you're like, no, it wasn't required. I'm never gonna use it in my whole life until next year when you figure out everything's linear algebra. But it's this, like a rotation matrix. Oh, if I could write it correctly. Going from A1, A2 back into E1, E2, you can kind of convert this way. If you're trying to remember how do I rotate a vector? And again, this is Just for your information, bonus kind of material. And so last time, what we did was say like, all right, if E1 is this and E2 is that, I can just plug it straight into my original definition of like, get rid of the E1s by the A1, A2 definition, and get all the E2s gone with that A1, A2. So now I've got RPO is, what was it, 2.3, 3.1. And there we go. Then the rest is like combining those terms, right? And then you'll do some math and figure out that our A1 term got bigger, and then this vertical component got smaller. And again, there's more than one way to do this. It's a geometry problem. There's tons of like proofs and stuff that you can do. This is one way, like just with basis vectors. Benefit of like looking at those basis vectors is it doesn't matter what vector you're dealing with. You don't have to turn it into like a trig problem, or at least the trig problems are all based on just the coordinate system, not the vector itself. And that, oh, not that one. Do we want to just grab this again? So we're done here. Done. When we say polar coordinates, what does that mean? What comes up? Yeah. Some kind of r and theta. Why r and theta? What's polar about that? Yeah. Yeah, so like general kind of idea is like we're trying to keep track of where, so the theta is just telling us a direction, and then r is telling us how far away from some origin we are. You can have multiple polar coordinates, like we could have more than one origin. In this case, it's the same origin, but different angle is measured differently. So how do you write the polar coordinates here? What does it even look like? Like how do I before we were writing a vector like this, how do I do that with polar coordinates? What does that vector look like? R? Yeah. Oh, an arc? Okay, maybe an arc, something like that. R and theta, okay. R and theta. So give it a shot. What is this? We're trying to write that polar coordinates. What does it look like? How do you keep track of radius and direction?
Yeah, that's it, we're just thinking kind of thing. Yep, that would work. Yeah, yeah.
What does it look like when you write down, this is my polar vector? How do you write that?
Oh, as a polar coordinate?
Yeah.
Isn't it like arc cosine theta, cosine theta, stuff like that?
Okay.
It's something like that.
Yeah, that would put it back into like Cartesian.
Right. I guess, yeah.
Yeah.
Or is it like r like pi over 2, pi over 4?
Okay. So you have like radius and angle.
Yeah. It was like,
You never think of like
yeah.
I know, yeah. Maybe, yeah. Do it at some point. That's this. Yeah. Oh, okay. That is, yeah, you're right. But it's just a little bit. Yeah.
the same line, like,
Oh, add an angle?
Yeah.
That can work, yeah.
this is right.
Alright, so it seems some agreement that the magnitude, like distance away is like 3.9, 3.8 something. Let's call it 3.9. So that's our magnitude. And then I've seen different ways of talking about direction. So some of the, at least like this is kind of asking us for, and I think people said the angle was like 53, something like that. So I've seen this a little bit. Was it 53 or no? Something like that. So I've seen some people kind of like track it like this, of like, I have a vector, it's got 2 components in it. To me, this is a little misleading because it seems like the vector has an x component of 3.9 and a y component of 53, which is not what we want. Like, that changes the magnitude. Oh, go ahead. Yeah.
So I have method of sparse PO equals 3.86 cosine of 23 degrees A1
Okay.
plus 3.86 sine 23 degrees A1 or A2. Sorry.
Okay. So another way is we could write. Oh, give me my mouse back. There we go. So instead of this, I'm gonna write it in terms of like E1, so we still have that same. Yeah.
I'm just confused how they got 53 correct.
Is it not 53? What's the angle?
No, I just don't know how to get there.
Oh, how to get the angle?
Yeah.
We know a lot about this thing now, because we're beating this horse just to a pulp. We know that this is hypotenuse 3.9. We know this is adjacent of 2.3, and this one is 3.1. And then if we want to find that angle, we could say sine theta is 3.1 over 3.9, or cosine theta is 2.3 over 3.9, or tan theta is 3.1 over 2.3. So we have, they're all gonna lead us probably to the same answer, because it's all quadrant 1. So yeah, invert any of those, like take the arc sine, arc cosine, arc tangent. So what do we think about like this one? Is this capturing polar coordinates? No? Why not?
I feel like you're describing it because of X and Y.
We're still back to like E1, E2 components. So it's closer because now we do have like, here's our magnitude and here's a direction, but we're still describing it as E1, E2. All right, so I'll lift the curtain, we'll look behind. (3.9 ER). There's some unit vector that is a radial vector. That's your position. Like, that's it. That ER vector is different. Like, if we change the angle, it might have, but it's always pointing at that point. And that's like a definition, at least for position, that is the definition for like a polar coordinate position. It only ever has one component. It's kind of nice, kind of cool. So this ER is always pointing this way. Yeah. And how ER is defined, like if you're trying to figure out like what direction is it in my Cartesian system, it is that like cosine, sine, E1, E2, kind of like that. What is this, number C, part C? So what's the polar coordinates in frame A? Which one?
It'd be the same thing, but you have a theta of 30 degrees west.
Yeah, so it changes what our angle of, like our angle 0 is pointing in a different direction, but our position is still 3.9 ER. Like it didn't change, because we didn't change how far away we are. All we did was change like what angle. So it's still 3.9 ER. And if we want to keep track of like where is that ER, then we would say that it's that cosine, what would that be, 23? Oh no, I guess, is it E1? Anyway, no, yeah, A1. There we go. This is one way to do it. So the reason that I'm kind of hammering this home is that it really helps to understand that polar coordinates position is always one component. Like you only ever have one component. Your unit vectors change because no matter where, because if you're moving, then the unit vector has to move with you, but it's always just describing magnitude along that ER direction. I'll pause for questions. The questions that you don't even know you have yet. Yeah.
Why don't we describe it as two terms and theta?
Why not two terms?
3.9 would be like an any 3.9 orientation.
Yeah, and so the goal with the polar coordinate system is it changes where the math, like when you have to do like trig kind of math. Because if I'm always saying like I have a unit vector pointed at my point of interest, then all that trig is happening in my definition of my coordinate system instead of trying to manually fit like circular problems into square holes. But that's doesn't make a lot of it. As you start using polar coordinates, you start seeing like, oh, this makes sense. Like this is much better. It doesn't mean that like velocity doesn't have to be radial, right? You can move in a straight line up and down and describe it with polar coordinates. It's just things change. Things are different. We just have to describe velocity in a different way. And we'll get to that. We'll try it out. And $323. So we're going to skip over a bunch of stuff and get down to 323, and we'll jump right back into polar coordinates. Well, I guess I already said something. I said jump into polar coordinates, but you can do this problem however you want. So we're thinking about a pendulum, but the pendulum can stretch. So the question is, first question is, how many degrees of freedom does a pendulum like that have? 2? 2? Why 2? Hinge and a spring, like the different parts that are moving? Yeah. Okay. Oh, you're thinking like hinge can rotate, spring can stretch? Yeah. I like that. Yep. Yeah, so you can think about like what are the moving parts? Like we can rotate this way and we can stretch along that way. Okay, makes sense. Yeah, another way is like if we fix the angle, like if the angle is only up and down, if it's 0, like if it has to be hanging straight down, we can still stretch basically to any length because it's just a linear spring. In reality, springs have some constraint, not a constraint, but like they can only stretch so far, but it doesn't constrain motion, it just creates a bound, like how much we can move. So 2 degree of freedom. All right. This is our first real like introduction. What is an equation of motion? Have you heard this term before, or do you remember it? This is the real like core of dynamics, equations of motion. Can you go from free body diagram and constraints to an equation of motion? Everything else is like differential equations or linear algebra, like all these other things, but the core like engineering part is, can you recognize 1, how many equations you need, and then 2, what they are? So, what do we think an equation of motion is? Yep. An equation that describes motion, all right? It's got to do something, right? Some kind of like motion description. Yeah. Okay, so motion is defined by forces, at least, so we're in it. This is Newtonian mechanics. Things don't move without force. So somehow force and motion are connected to each other in our equation of motion. All right. So if we have 2 degrees of freedom, we can have hundreds of forces acting on this thing. But with 2 degrees of freedom, how many equations of motion do we have? 2? It's 2. Oh, 3? Why 3? No? Okay. I like 3. Yeah. 3 is a good guess. But at the end of the day, if you have 2 degrees of freedom, you gotta have 2 equations of motion. Sometimes they're like coupled, like they're linked together. Sometimes they're decoupled, but we need 2 equations. So we can we should be able to get there with just like sum of the forces x, sum of the forces y, because that'll give us 2 equations. If it was like 3 degrees of freedom, then we need more, maybe like moments or sum of the forces z or something. So the main thing here, main learning part there is like, if you recognize there's 2 degrees of freedom, there's gonna be 2 differential equations describing equations of motion, how force and motion are connected. All right, so now I said polar coordinates, but what do you say? How do you want to describe, what coordinates do you want to use for pendulum motion? Okay. Okay, and then something about like, because the bigger the radius, the more the spring is stretched. And then what do we want to say is angle 0? Flat? I like that. Kind of like this. that's like my ER, that unit vector, at least if we're using if we decide polar coordinates, that's my unit vector. So the position, like R times that ER, that unit vector ER. Okay, now it's up to you. We chose a coordinate system and we said this is how we're going to define motion. It's either radius is changed, I mean it can be both, but radius can change and angle can change. What are the forces acting on it? And then what are the accelerations from those forces? And then, yeah, after we draw that, I think we'll wait till next time to look at what the equations in motion are.
Just a little question. Gravitational force. And then I was gonna do Hooke's law.
Okay.
Or something like that.
Okay. Where's the normal force coming from? Okay, that's all right.
Yeah, long night.
Okay, yeah, what do you want to do?
I feel like I can use equation models, if like forget that the spring exists, be like it's just tension.
Yep.
Yeah, so what's the tension? Yeah, well then we can just make another equation, right? So another equation for the spring, that is the spring, and we can equal that to the tension of the ball.
Okay.
So once you substitute that in,
Oh, so the two equations, so that one's called like a constitutive equation, and then you use like Hooke's law, so that'll define like the force of tension in terms of position, so it helps, helps that part, but we still need something relating, what is the angular velocity in terms of tension and gravity, or if there's anything else you're trying to explain. And that one's like, those are there. Just the space motion. But yeah, that's a good clarifying, because you can use whatever. You can try to say like, okay, a squared plus b squared is c squared, but it's not going to add. That might have like a constraint or something, but not negation. Yeah. I didn't see anybody jump into like, oh, let me add some drag into this. So I'm fine with that. We'll just have like slow motion, like not like super fast stuff. There was a question, actually a very good question. Is the force of the spring always pointing back towards the origin? No? You don't think so? Yeah, so it is, so as the angle is changing, force of the spring changes direction. But then there's also the question of, does it need to reverse directions? Like if we stretch it a lot and then it bounces up, so it compresses the spring and then pushes it back out. Do we need two vectors? Two vectors? How much it compresses? Okay. So I can tell you how I deal with it. Again, all this is anecdotal. I mean, it works, and it's a nice system. A lot of people use it. So here, if we back up to our coordinate system, ER is always pointing towards like a stretched spring. So if the spring is unstretched and I pull it along a positive ER direction, is the force of the spring positive or negative? Is it pulling up to the origin, or is it down towards the ball, our pendulum? It's up and to the left, which is a negative ER. So Fs is always, we can draw it as up that way. If we happen to have a compressed spring, then that R minus L will be a negative number. So it will be a negative times a negative, and we end up with positive force. So we don't have to worry about it as long as you're keeping track of positive displacement and negative force. Like it's got to be inverse to each other, and then you're good, golden. This was the part that I didn't see anyone venture a guess here at what does acceleration look like. Like our kinetic diagram, we want to say MA. What is MA? How many components do we need to describe MA? We need two, because it's 2 degrees of freedom. So we need, there's only one vector, but we're going to describe that vector in 2 different components. Where are they pointing? This is it. As soon as we do this, we're done, and it's the weekend. Or maybe you have another class, but you can skip it because you worked so hard in this class. Just give them a Professor Cooper. Like Professor Cooper said I could skip my next class. I'm going to happy hour.
I feel like at least one of the forces would be pointing in towards like the joint there as kind of like a spring force and also centrifugal. Not force, acceleration.
Oh, the acceleration. Okay, all right. So you want to say like a MA kind of centripetal force, centripetal?
Yeah, maybe.
Something like that. Yep. Yeah, and that is one way. That one's a little hard because we don't know that it's traveling like in an arc. So we don't know the radius right now, at least because the spring is like stretching and it's swinging. So the radius might be changing. So it's hard to know exactly where MAC is pointing. But that is one way. Yeah. And you can always use that, but sometimes it's just harder. I do like that. But something like radial, that radial component, like there's either something pointing in or pointing. So we chose we chose cylindrical coordinates to begin with, or maybe you were like voluntold to do cylindrical coordinates. So one of the components is just how fast is it moving away from the origin, like MAR. What's the next component? Where does that one point? An MA theta, yeah? So in this case, and again, like I drew my theta, I do the same thing every time so I don't like mess it up, and there's just like a system to it. You can define theta, you can, as we saw in the last problem, theta can be any 0 direction you want. But if this is my theta, and increasing theta moves it up and to the left, MA theta is 90 degrees counterclockwise rotate from MAR. And from here, the next step is like math to get to what are the equations of motion, but we did like the main start. We identified degrees of freedom, define our coordinate system, we have all our free body diagram. We're in good shape. The rest is just a whole bunch of math, which everybody loves, so we're good. We'll just have fun with that next time on Monday. All right, thanks a lot.